Right, waves. This is from the topic of refraction, diffraction, and interference. So, we're starting with interference and we'll see how far we get, depending on how long this should be. So, path difference and coherence. So, coherence. Interference happens when any two waves are superimposed on one another. But in this case, it's a really messy wave pattern. To see a clear wave interference pattern, we need two waves that are coherent. That means they have the same frequency and wavelength. The amplitude doesn't have to be the same, it's just frequency and wavelength. Path difference. The path difference between two waves is the distance in length travelled by the wave to get to a certain point. And path difference and interference. So for two coherent waves, if the path difference is a multiple of lambda, the waves will be in phase, and we'll see the constructive interference as path difference equals n times the path difference, lambda. If the path difference is a whole number plus half of lambda, the wave will be exactly out of phase and we'll see destructive interference. So constructive interference is when one wave is like this and the other wave is also like this. Or destructive interference is when the maximum and minimums are opposite. So when one's at amplitude, the other's at trough. So what kind of interference is produced when we have a path difference of n plus a half destructive? Perfect. So, the most famous person of one of these experiments was Young and his double slit experiment. This was the interference from two monochromatic coherent sources. Monochromatic means all light has the same wavelength. So what he did was, to observe the interference between two coherent waves, he shone a laser through two slits. The laser produced monochromatic coherent light. So same wavelength, same wave, same frequency. The two slits then acted like identical sources of the laser light. The slits had the same size and that allowed it to be comparable to the wavelength. So here the laser was shot through the light, well through the slits, and it came out on this screen with this pattern. So this was how it went basically. So there were a series of dark and light fringes. When light passes through the two slits, it will diffract and cause an absorption pattern. It's not an absorption pattern, is it? I don't think it's an absorption pattern. Yeah, it's an interference pattern, yeah. So the slit must be a similar size to the wavelength of light in order for the waves to something and produce a interference pattern. For the waves to what? For the waves to something, to, well, the premise is to join up really. The slits must have the same size to be comparable, same size and to be comparable to the wavelengths to diffract it. To diffract. So Fringe and Young's double slit experiment. We can calculate the spacing of the fringes seen in a double slit experiment. Fringe spacing. To calculate the space between bright fringes in a double slit experiment, we use W equals lambda D over S. The fringe spacing is W. Wavelength is the dimented H. The spacing between the slits is S, and the distance from the slits to the screen is D. Averages over many fringes. Normally the fringe spacing is very small. This allows our measurement to be a lot more accurate. Using white light. We can use white light instead of laser light in the double slit experiment. Instead of clear bright and dark fringes, the middle fringe would just be a white light, and then it would be like the entire spectrum of colours. So the outer fringes of a diffraction pattern are spectrum of colour. Yellow diffracts the least, so it's closest to the centre. The outer fringes of a differentiating pattern are spectrums of colour. Yes, they are. Yellow diffracts the least. Does yellow or is it red that diffracts the least? But I'm pretty sure it makes a rainbow where that's the middle and that's yellow doesn't diffract the least. So what diffracts the least here? In this one, it's purple. Surely it's red. It's blue. So it's the opposite to a rainbow. Which two quantities in fringe spacing W is directly proportional to the distance from the slit to the screen and the wavelength. So something interference will occur when path difference is equal and an odd number of half wavelengths. So path difference is equal but odd number of half wavelength. So it's that destructive interference because it's an odd number and a half. So why do we only use one source? Because it's difficult? Nope. Light intensity is the same, so light is coherent. Yes. Next, W equals d lambda over s. What corresponds to fringe separation? Well, W, D, or S. So S is wavelength, so it can't be that one. And that is fringe spacing. That one is fringe spacing. So, is that the same? Yeah. Fringe spacing is the same thing. So, waves must be something and something monochromatic. Waves must have a path difference of n lambda for constructive and waves must have a path difference of that for destructive. So waves must be some coherent. Perfect. And that is interference 1. Now interference 2 will be next. We got one wrong there, and that took 7 minutes. So interference 2 should theoretically just be easy. I believe it should be a smaller version of interference 1. So let's get it. Laser safety. Lasers are dangerous and need careful handling and use. That's because it could go in your eyes and could hurt your eyes. Wear protective clothing and eyewear, yeah. Internationally agreed to be used outside and inside laboratories and stick to institutional safety requirements. And dangers, it could hurt your eyes. That is literally what there is. So with high powered electrical shocks, the body's natural aversion reflex, the eye will automatically look away from the bright source. With high power, is too slow to prevent damage to the retina. So that is here. So with high power, it's not electric shock. We're talking about lasers, aren't we? That should have been very obvious from the start. So wear protective clothing and goggles. Lasers used clearly instructed. Nope. Don't point in people's eyes. Yeah. Laser use clearly something. Laser use clearly. Clearly what? Laser use clearly. Red. Signed. Oh. Wow. So, scientists have changed and updated their understanding of the nature of electromagnetic radiation over time. Newton's, Huygens, Young and Einstein are prominent scientists in the theory of light. Newton's corpuscles. In the 1600s, Newton theorized that light is made out of corpuscles, which are little packets of light. Huygens stated that they're waves. Young proved that they're waves. Einstein proved that they're photons, thus being not waves, so being particles. And Compton scattering experiment, photon scattering, provide more evidence for it being a actual particle. So the history of MR radiation. So first of all was Newton, then it was Hudge, whatever the hell his name is, then it was Compton's scattering. No, Compton was last, I think. Yeah, Compton was last. So it was Young, Einstein, Compton. There was also Hudge, whatever his name is. What was the name of the particle of light? Corpuscles. I don't know how to spell it though. But it was corpuscles. Or corpuscle, whatever the hell. Corpuscles. Corpuscles. Muscles. How do you spell the stupid word? Corpus. Pus. Les. So interference of sound waves. Interference can be observed in all types of waves, including sound waves. Move microphone. By moving the microphone from one side to another, we can measure constructive and destructive interference by whether the noise is loud or quiet. Experimental setup. So to be able to do this, you can use the setup here. The two sources need to be coherent, meaning that the same sound must be played at the same time from the same speaker. So the something sound must be played out of each speaker to make sure the waves are coherent. The same sound and then coherent. Perfection. So why do the sound waves from both speakers have to be coherent to cause interference? Oh no. In order to produce a constant interference pattern, we play the same sound through two speakers to make sure that the waves are coherent. They're really pushing this agenda if you need to know what coherent means. We get it. So, which of these must you do while using a laser? Clearly signpost. Never point in people's eyes because that is so stupid. What experiment did Einstein conclude? The photoelectric effect. That's basically when you shine light, the energy isn't fully dissipated on everything, which means that it must be like light can't be a wave because waves always dissipate everything evenly, whereas this didn't. So the end of topic test. What kind of interference will this construct? Constructive. Perfect. So, which property of a wave is not required to be the same for two coherent waves? The amplitude. The amplitude just add up. What term describes light of equal wavelength? Coherent. Light of equal wavelength. That's a good question. Let's find out what it actually means. It means boom. What term describes light of equal wavelength? Same. Monochromatic, yeah. What size must the two slits be relative to the wavelength for the same? Well, no, they have to be the same to make it fair. What kind of fringes are produced by the double slit experiment? So these are alternating. What kind of fringes? They're fringes with gaps in them. Right, dark. What do you mean? We're the following is a correct equation, so it is this one. Perfect. Which of the following should you never point your laser at? Your eyes. Oh no, your shoes. The shoes are going to complain. What should you wear while working with high-powered lasers? Protective eyewear to be able to save your eyes from when we don't point the lasers at you. Who proposed the theory of wave fronts? Wave fronts. So Newton did it, and then because Newton did it, but he didn't do wave fronts. So it is the Hudge whatever the hell guy. Okay, I know who it is. Yeah, Oh, it is actually spelled how I pronounced it. Name one phenomenon which shows the particle nature of light. Name one phenomenon that shows the photoelectric effect. Yeah. Which of these statements are true? Sound waves can interfere with one another. Yes, they can. Light waves can interfere. Cannot. They can. And waves can. All waves can interfere with each other. What does constructive interference of a sound wave sound like? The same. Oh, louder. Yeah, louder. But it's like the amplitude gets higher. So that is interference.